Very good morning, everyone. This is Krish Patel. I welcome you all to this course on VLSI, very large-scale integration. This subject holds a foundational place in modern electronics and semiconductor design. Whether we're talking about smartphones, computers, automobiles, industrial machines, or medical electronics, none of these systems will be possible without VLSI. VLSI refers to the process of integrating millions and now even billions of transistors and other electronic components onto a single chip made of semiconductor material, usually silicon. This technology allows us to design systems that are smaller in size, faster in operation, more power efficient, more reliable, and cost-effective for large-scale production. In fact, the evolution of modern electronics, from large room-sized computers to palm-sized smartphones, has been made possible almost entirely due to advancements in VLSI technology. So, here's what we'll cover today. We'll start with the definition, move through its history, importance, applications, and then explore how it actually works, the design process, the types of chips, and finally the current trends and what's next in this field. What is VLSI? VLSI, or Very Large-Scale Integration, refers to the process of embedding millions to billions of transistors and other circuit elements onto a single chip. These chips are called integrated circuits, ICs. This level of integration has made it possible to reduce the size of devices drastically, while increasing their processing capability and minimizing their power consumption. To understand the significance of VLSI, we must briefly look at how electronic circuit design evolved over time. Initially, circuits were built using discrete components, each performing a single function and connected with wires. This made the systems large, slow, and prone to failure. Then came small-scale integration, SSI, which allowed a few logic gates to be placed on a single chip. This was followed by medium-scale integration, MSI, hundreds of gates per chip. Large-scale integration, LSI, thousands of gates per chip. And eventually VLSI, which integrates millions of gates onto a chip. This technological advancement was made possible by the invention and continuous improvement of the MOSFET, metal oxide semiconductor field effect transistor, which allowed miniaturization without compromising performance. In 1971, the Intel 4004 microprocessor, which had approximately 2,300 transistors, marked the beginning of commercial VLSI. Today, processors have crossed the 100 billion transistor mark in a single chip, demonstrating the scale and potential of this technology. Let us look how VLSI has transformed how we design and build electronic systems. It is important not only because it reduces the size of systems, but also because it improves the speed, reliability, and efficiency of those systems. It allows manufacturers to create faster computing systems, use less power, reduce costs through mass production, and offer greater functionality within a smaller footprint. This is why devices like smartphones, laptops, wearable electronics, and industrial automation systems can perform complex tasks while maintaining portability and efficiency. The applications of VLSI are widespread and span across every major industry that depends on electronics. Some key areas include consumer electronics, smartphones, tablets, televisions, smartwatches, automotive electronics, engine control units, ADAS, advanced driver assistance systems, infotainment systems, communication systems, 4G per 5G modems, Wi-Fi chips, satellite communication systems, medical electronics, pacemakers, diagnostic tools, portable health monitors, embedded systems, home appliances, industrial machines, robotics, aerospace and defense, navigation systems, control units, surveillance devices. In summary, VLSI is at the heart of almost every modern electronic product. There are three primary reasons why VLSI enables such advancement in technology. High integration density. VLSI allows a high number of components to be integrated on a single chip. This leads to smaller system sizes, which is essential for modern portable and embedded devices. Scalability. As fabrication processes improve, we are able to shrink the size of transistors and fit even more components in the same chip area. This allows systems to be upgraded and made more powerful without increasing their physical size. Advanced fabrication technique. VLSI depends on highly precise manufacturing methods such as photolithography, ion implantation, and chemical vapor deposition, which are carried out in controlled environments called cleanrooms. These techniques enable extremely small feature sizes, allowing chips to function at high speed while consuming very little power. Designing a VLSI chip involves a well-defined process. The key steps are: specification, define what the chip is supposed to do. Architectural design, decide how different functional units will interact. RTL design, write the logic using a hardware description language like Verilog or VHDL. Simulation and verification, ensure the logic is functioning correctly before physical implementation. Synthesis, convert RTL code into logic gate-level netlists. Physical design, determine the placement and routing of components on the chip. Fabrication, manufacture the chip using semiconductor processes. Testing and packaging, check the chip for defects and prepare it for use in products. Each of these steps requires the use of specialized tools and follows strict design rules to ensure functionality and manufacturability. VLSI chips can be broadly classified into digital VLSI chips. These handle binary logic and include processors, memory, and controllers. Analog VLSI chips. These handle real-world signals such as audio and voltage levels. Mixed signal chips. These combine both analog and digital components. They're used in smartphones, sensors, and communication devices. RF chips. These are used for wireless communication like Wi-Fi, Bluetooth, and mobile networks. As technology continues to advance, we are now moving towards the next level of integration, often referred to as VVLSI, which stands for very, very large-scale integration. This term is used to describe systems that integrate more than 1 billion transistors on a single chip. VVLSI is not a formally defined industry standard, but it represents the scale at which modern processors and SoCs are being developed today, particularly in applications like AI processors, data center chips, and high-performance computing. VVLSI continues the trend of miniaturization, increased speed, and reduced power consumption, using advanced transistor architectures like FinFET, GAAFET, and 3D stacking. In simple terms, VVLSI is the practical extension of VLSI, pushing the boundaries of what a single chip can do. In the next lecture, we will begin with digital logic design, which is the foundational layer upon which all VLSI systems are built. Thank you for your attention.